In problem number 19, we are given the graph of a function of two variables, shown here in blue, and a point on this graph, point A shown in red, and we need to make a determination of whether the derivative, the partial derivative of z with respect to x at the point A is positive or negative, and similarly for the partial derivative of z with respect to y at that point A, is it positive or negative? So before we approach this question, let's recall how one could determine whether the derivative of a function of one variable is positive or negative by looking at the graph of the function and the point on that graph where the derivative is evaluated. So here's an example of a graph of a function y equals to f of x. The graph is drawn in the xy plane. This is a function of one variable, so the graph is drawn in the two-dimensional plane, xy plane. And let's recall that the derivative dy dx measures the rate of change of the y values when the x values are changed. This is the rate of change of y values with respect to the x values. Now let's look at the point A first on this graph. I don't know why I erased it. Actually wanted to show it to you. Okay, so let's say we're at this point A, and suppose we increase the values of x. If we increase the values of x, then the point A will move along the graph of this surface, a graph of this function, and you see the positive direction of the x-axis is to the right as usual, and you can see that the graph goes down at the point A. Therefore, if we increase the values of x, the point A will move to the right and down, sliding down the graph of the function. Now, when the point goes down, its y-coordinate, right, looking at the y-axis, the y-coordinate decreases. And so what we see then is that as x values increase, the y values decrease. And therefore, the derivative of y with respect to x at the point A is negative. By contrast, if we look at the point B, there, if we increase the value of x, then the point will move upwards. Its y value will increase, and therefore the derivative dy dx at the point B is positive. Now, let's return to our question on the practice test. The situation here is similar but more complicated, and the reason it is more complicated is, of course, because our function z now depends on two variables, x and y. Let's recall that the partial derivative of z with respect to x measures the rate of change of z values with respect to x. And when we calculate this derivative, we keep the value of y fixed. So geometrically, if we want to see or get a sense of what that partial derivative is, we would have to stand at the point A. We would need to fix the y coordinate and then increase the values of x. And what we need to determine is whether the point A will go up or down, whether the values of z will increase or decrease. Let's take a look at the various cross sections of this graph to get a better sense of how they look. Here's the surface shown in pink, located in the three-dimensional xyz space. The x-coordinate is in red, the x-axis is in red, the y-axis is in green, the z-axis is in blue. In addition to the surface and the coordinate axes, the graph, the plot here shows the xy plane shown in gray. Sort of helps to see the surface better. Note that half of the surface is located above the xy plane and half of it is below. Okay. So now we're looking at the surface from above. Okay. And now I will show you some cross sections. So first, let's consider cross sections consisting of points having the same x coordinate. These cross sections can be obtained by intersecting our surface with the plane perpendicular to the x-axis. So here's one such curve shown here in black. All the points that lie on that black curve, they all have exactly the same x-coordinate, but the y-coordinate varies, and that results, of course, as also in a different z-coordinate. Now, I will now change the x coordinate, that I will change the number that the x coordinate of all those points on the cross section are equal to, and that would make this cross section move. So bear with me for a second here. So if you change that number that you set your x coordinate equal to, you're gonna get a different cross section. Okay, so I'm gonna wait for that point to return to some good position, and then I will stop. Okay, now let me hide this cross section. Actually, let me now add a cross section of the surface by a plane perpendicular to the y-axis. So here's our second curve. Now we're seeing two cross sections, one by plane perpendicular to the x-axis and one by the plane perpendicular to the axis. Let me hide the first cross section, and similarly everything is similar here except for this cross section the y coordinate is fixed, and we can change that value, and that would result in our cross sections moving to a different position. All right, so I'm gonna wait for this curve to return to some convenient location, and then we'll talk about the partial derivatives. So let's return to the two different cross sections, one with the x coordinate fixed and one with the y coordinate fixed. Now we see that these two cross sections intersect at a point. Let me show you that point. So here's the point of intersection, point D. And let's say we want to analyze the partial derivatives of the function z at this point D. Now, if we want to concentrate if we want to think about the sign of the partial derivative dz dx, which of these two cross sections passing through the point D should we look at? I'll give you a couple of seconds to think about this question. You can pause the video and think about this, and then continue with the video to see if you answered this question correctly. Okay, so since we're looking at the partial derivative of z with respect to x, x is the variable that we're going to change, and then the other variable y will have to be fixed. And so we need to fix the y coordinate, and therefore I'm going to hide the curve that is not relevant. Now this curve that remains is the one that we need to look at. And now look at the positive direction of the x-axis. Here in this graph, it's to the left. If we go let our point move along the cross-section curve in the direction where the x-coordinate is increasing, we will see that the curve goes down. And therefore, the z values decrease as x values increase and the y values are kept fixed. And therefore, the partial derivative of z with respect to x is negative in this case. If we want to analyze the partial derivative of z with respect to y, everything is the same, except we have to look at the different cross sections. So let me now bring back the other cross section and hide the first one. And here again, the positive direction of the y-axis is important. And you can see that again, if we let our point D move in such a way that the if we let the point D move in such a way that the y coordinate is increasing, then we will see that the point goes down. And that means that the z values again decrease, and that partial derivative of z with respect to y is negative, as well as the partial derivative with respect to x. Now, let's return to our question. Here are those cross sections. You can see them. They're shown in thin black lines on the surface. These are the cross sections, and what we just need to repeat this process that I just explained for this point A on the surface. If we fix the value of y and increase the values of x, then we're going to be moving along the following cross section. Try my best to draw it. And we'll be moving in this direction right here. And you see that we're going to go down. The z values decrease, and therefore dz dx is negative. If we keep the value of x fixed and we increase the y values, then we will be moving along this cross section upwards. And because we're moving upwards, the z values will increase, and therefore the partial derivative of z with respect to y is positive. Let me write down the results. dz dx at the point A is negative, and the partial derivative of z with respect to y at point A is positive.